Good morning. In today's lecture, we shall discuss coherence. So, let us start by revisiting the main formula that we use in interference. So, the main formula, let me show you the main formula that we use in interference. It is shown over here. The intensity. So, we have superposed two waves E1 and E2. We have superposed two waves E1 and E2 to obtain a resultant wave E, and then we have calculated the intensity of the resultant wave. So, the intensity is the time average of E square. Right. So, we have calculated, we have superposed two wave E1, E2, and then we have calculated the intensity of the resultant, so which is the time average of the resultant E, and the intensity of the resultant is the intensity of the individual waves I1 plus I2 plus this extra term over here. The extra term which over here is 2 root I1 I2 cos phi 2 minus phi 1. It is this extra term, it is this term over here which is responsible for interference, and it is this term which is of interest. So, let us just again recapitulate how this particular term comes about. So, if I go back one step, so we are calculating the time average of the square of this and this note. So, we have this I1 which is the square of this, the time average of the square of this, then we have I2 the time average of the square of this, and then we have the cross terms E1 E2, which in complex notation is written over here, and it is this term that gives rise to the term responsible for interference. So, let me just remind you how we which is the term that is of interest. The term responsible for interference arises from this, from the time average of the product of E1 and E2, and we had assumed that both E1 and E2, so E1t, we had assumed that E1t in the complex notation could be written as a real amplitude, a phase phi 1 into e to the power I omega t. E2 could be written as E2 e to the power I phi 2 e to the power I omega t. So, there was an assumption that both E1 and E2 are of exactly the same frequencies. They have the same frequency and they have only one frequency. So, both waves, we have assumed that both the waves that we are superposing are sinusoidal oscillations of a single frequency, and these two frequencies are exactly the same. Let me recapitulate again what we had assumed. We had assumed that E1 and E2 are both perfectly sinusoidal oscillations of the same frequency omega, which allows us to write E1 and E2 in this form, and then we can calculate the time average of this product E1 E2, and this is 2 root I1 I2 cos phi 2 minus phi 1, where I1 is the intensity of this wave, I2 is the intensity of this wave, phi 2 is the phase of this wave, phi 1 is the phase of this wave. So, we are focusing in the expression for the intensity. When I superpose two waves in the intensity expression for the intensity, I told you that it is this term which is responsible for interference, and we are focusing on the origin of this term. How did this term come about? And I told you that this term comes about when we calculate this time average, and this involves the assumption that both E1 and E2, both the waves are monochromatic. They have a single frequency which is same for both of them. Now, there is a very important fact which I should tell you, that you really do not have waves of a single frequency. Such things do not really exist. You always have a spread in the frequencies. So, when in reality it is not possible to produce waves of a single frequency, there is always a spread. So, when we deal with real waves in some real practical situation, there is always a spread in the frequencies. The analysis which we have been doing till now is a mathematical idealization which makes it simple to handle the situation. So, it makes the calculation simpler. If we assume that there is only a single frequency in the two waves that we are superposing, or in any other situation where we have a wave, it is mathematically easy to handle a situation where there is only a single frequency, but in reality there never are waves of a single frequency. So, we have to at a certain instant, for certain purposes, we have to take into account the fact that there is a spread in frequencies. So, in today's lecture we are going to ask the question, what is the consequence of the fact that there is always a spread in the frequency? How is this going to affect my results? So, in this particular case we are looking at interference. So, how is the fact that there is going to be a spread in frequencies, how is this going to affect the basic formula that we use in interference? The basic formula is the one is what is shown over here, and the term which is responsible for interference is what I have shown over here. So, we are going to discuss the consequences of the fact that both the two waves have a spread in frequency. We are going to discuss the consequences of this fact on this particular expression over here, which is the term responsible for interference. So, before we address this very important question, let us first discuss what happens if there is a spread in frequency. How does the wave look as a function of time if there is a spread in frequencies? Okay. So, we have already discussed this when we were discussing coupled oscillations. When we were discussing coupled oscillations, if you remember, we encountered a superposition of two oscillations, one a slow mode and a fast mode, right. So, we have already encountered a situation where we have a superposition of oscillations of two different frequencies. So, let us look at that again. So, we will consider a situation where E t, and let us work in the complex notation. So, the wave which we are looking at a fixed point is an oscillation that is a superposition of two different frequencies. So, we will write it like this: A1 e to the power I omega t plus e to the power I omega prime t. Now, we can define the mean frequency omega bar to be omega plus omega prime by 2, and the difference in frequencies delta omega omega prime minus omega by 2. Then this wave can be written as A1, and we will write omega in terms of the average frequency and the difference in the frequencies. So, if I write omega in terms of this, it is going to be e to the power I, then I will have omega bar minus delta omega by sorry, this delta omega does not have this 1 by 2 over here. The difference in frequencies is omega bar minus omega prime minus omega. So, we can write omega as this minus half of this. So, the first term over here can be written like this, and the second term can be written as e to the power I omega bar plus delta omega by 2 into t. So, we have this. So, the same electric field, the same wave which I had, which was over here, which was a superposition of two different frequencies, can also be written like this, and this can be written as A1. Now, I can take e to the power I delta omega by 2 t common outside. If I take it common outside, then I will get a term which is 2 cos delta omega by 2 t e to the power I omega bar t. So, what we have done here is just a little bit of algebra, by means of which we had written the wave, which was a superposition of two different frequencies, in this form. Now, notice that here, if we assume that omega and omega prime are very close, over here we have two oscillations which we can interpret as follows. We have already discussed this interpretation in the context of the coupled harmonic oscillators. We have a fast oscillation at the average frequency omega bar. So, the average frequency omega bar, which is omega plus omega prime by 2. So, we have a fast oscillation at the average frequency omega bar with some amplitude, which is the term within the square brackets, and the amplitude also changes with time in a slow fashion. So, there is an amplitude which changes on a slower time scale. The angular frequency corresponding to the time scale at which the amplitude changes is delta omega by 2. It is a difference in the frequencies divided by 2, and we have assumed that these two angular frequencies are very close. So, this delta omega is a small number and delta omega by 2 is a smaller number. So, we can interpret this as a tilde t e to the power I omega bar t. So, we can interpret this as a complex, as an oscillation at a frequency omega bar, fast oscillation at a frequency omega bar with complex amplitude a tilde t. The complex amplitude itself changes slowly with time. So, the amplitude itself changes slowly with time, and in this particular case the amplitude is A1 2 cos delta omega by 2 t. So, the amplitude itself does oscillations with angular frequency delta omega by 2, which is very small. So, it does slow, it changes very slowly with time. So, this is what we learned if we have a superposition of waves of two frequencies. So, if my wave, I have a wave, if that wave has two frequency components, then we see that we can think of it as doing fast oscillations at the average frequency, and the amplitude of that fast oscillation changing slowly with time, with and the amplitude changes with angular frequency delta omega by 2, the difference in the two angular frequencies. So, from this situation, let us directly now jump to a situation where we have many waves which are superposed. So, we have a wave many frequencies which are superposed. We have a wave which I represent as E tilde t, E1 tilde t, let us say. I have a wave, and this wave is the superposition of many frequencies centered around the average frequency omega bar, and the frequencies are spread out in a small interval delta omega around the average frequency omega bar. So, let me again tell you what E1, this oscillating wave, what this wave E1 t is. E1 t is a superposition of oscillations of different frequencies, and these different frequencies are in the range of angular frequency delta omega centered around the value omega bar, right. And the question that that arises is now, how does the wave look like as a function of time? And our analysis with two frequencies, here we just consider two frequencies, tells us that the resultant is a fast oscillation with the frequency omega bar, angular frequency omega bar, and the amplitude changes slowly with angular frequency delta omega by 2. So, let me tell you without any proof, but with sufficient motivation which I have already given you, that we will expect this to have a very similar behavior. The resultant oscillation is going to be a product of two terms, one a fast oscillation at omega bar, which is the average frequency of all the different frequencies that have been superposed. So, the wave is going to execute fast oscillations at the average value omega bar. The amplitude of the wave is not going to be a fixed number. The amplitude of the wave is also going to change in time, and the amplitude A tilde t is going to change on a time scale t, which is approximately of the order of 2 pi by delta omega. So, if we have a wave E1 t, which is a superposition of many frequencies, all of these frequencies which we have, which are superposed into this, are spread out, these frequencies are spread out in a range delta omega centered around a mean value omega bar. If in this situation, then the resultant wave can be written as, can be thought of as a fast oscillation at a frequency omega bar, with the amplitude of this oscillation changing slowly on a time scale t, which is 2 pi by delta omega. Okay. So, I have not given you any proof why this should be so, but I have given you sufficient motivation by considering a superposition of two frequencies, and showed you that there is sufficient motivation to believe why this should be so, and you can actually do a little more of mathematics, considerably more mathematics, and actually arrive at at a conclusion like this. So, let me now show you a picture of what the waveform will look like. So, what is shown over here is as follows. So, let me explain to you what I have shown you over here, what is being shown over here. So, what is being shown over here is as follows. We have superposed. Okay. So, before that, so the bottom curve over here, the one in blue, shows you a wave which is oscillating at some angular frequency omega bar. So, the bottom curve over here shows you a wave which is oscillating at a particular angular frequency omega bar. The value of omega bar here is not very crucial. The discussion does not critically depend on the value of omega bar. You can determine the value by just looking at the curve and using the values along the x axis. the main point is that this is a pure sinusoidal wave with a fixed angular frequency omega naught. The upper curve over here has been produced by superposing 2000 different frequencies in the small range of angular frequency delta omega, centered around this value, same value omega naught, which has been used to plot this. So, we have superposed 2000 different frequency components in the frequency range delta omega, centered around the same value used for this curve, such that delta omega by omega bar is 0.2. So, the spread in frequencies is 20% of the central frequency around which the values are spread. So, we have superposed 2000 different frequency components and plotted the resultant. So, the first thing that you should note is that the resultant shows fast oscillations at the same frequency as this, at the central, at the average value which corresponds to this. So, the fast oscillations over here have the same frequencies, they have nearly the same frequency as the oscillations in this particular wave, because here we have superposed 2000 different frequency components centered around this same value. So, the fast oscillations here are at the mean frequency, mean angular frequency, which is the same. So, you can see that the fast oscillations here look very much like the oscillations in the lower curve, but the amplitude of this oscillation changes with time, whereas this amplitude, this is a pure sinusoidal, the amplitude of this remains fixed. The amplitude of this oscillation changes slowly with time. The time scale of this change in the amplitude, we have just seen the, I have just told you that the time scale at which you expect the amplitude of the oscillations to change is 2 pi by delta omega. Okay. So, you see here that the amplitude is changing, and the amplitude is changing at a scale which is quite large compared to the fast oscillations. Let us ask the question on a time scale which I have shown over. So, this you would call the time scale of the change of the amplitude, and this time scale over which the amplitude is changing is much faster than the time scale at which you have the fast oscillations. Let us now ask the question how many fast oscillations do we expect to get in the time over which the amplitude changes, right. So, the amplitude changes on a time scale approximately 2 pi by delta omega. The fast oscillations t occur on a time scale 2 pi by omega. The question we are asking is, in this time scale, how many oscillations do we expect to get? So, this will be t by t, capital T by small t would tell you the number of oscillations you would get on the time scale at which the amplitude changes, and this is approximately, this is of the order of omega by delta omega, which is in this case 1 by 0.2, which is of the order of 5. So, you would expect in this particular situation, if what I have told you is correct, you would expect to get 5 fast oscillations in the on the time scale at which the amplitude changes slowly. So, let us check if that is indeed correct. So, you can look at the graph, the upper curve, and see that the time scale over which the amplitude changes. So, one time scale over which the amplitude changes would correspond to something from here to here, and you have 1, 2, 3, 4, 5, 6, 7, 8, around 8, which is of the order of 5. You have 8 fast oscillations on the time scale at which over the time scale in which the amplitude changes. Okay. So, the crucial point over here is that when you superpose a large number of frequencies spread in a range delta omega around a central value omega bar, the resultant wave has a fast oscillation, you can think of it as a fast oscillation at the mean angular frequency omega bar. The amplitude of this fast oscillation changes slowly with time, and the time scale over which this amplitude changes, capital T over here, is decided by the spread in the angular frequencies delta omega, and it is of the order of 2 pi by delta omega. Not only does the magnitude of this amplitude change, you can see that the magnitude of the amplitude changes, it is larger here, it becomes smaller, etc., but also the phase of the oscillation changes slowly with time. Notice that to start with, the upper curve and the lower curve are exactly out of phase, but if you look at the two over here, you will see that the two are oscillating more or less in phase. So, the phase of this particular curve has also changed slowly over time. So, what I have been trying to do over here in the past few minutes is to convince you that when I have a wave which is a superposition of many frequencies in a small band delta omega around a central value, the resultant wave is a fast oscillation at the central value omega bar, at the mean value omega bar, and the amplitude now also changes with time on a time scale 2 pi by delta omega. Okay. Now, the question is what is the consequence, the question that we were interested in to start with. Let us get back to that question now, and the question was, what is the consequence of this spread in frequencies on this particular formula over here, which is the main formula that we use in interference. Right, we have to take into account the effect of the finite frequency spread of the wave, and we are taking into account this effect by asking the question, what is the effect, what is the consequence of this effect on this particular formula, which is the central formula when we discuss interference. So, let me tell you the answer, and then we will discuss it in some more detail. The main consequence of this spread in frequencies, so there is a spread in frequencies in real waves. In any real situation where we have waves, there is always going to be a spread in frequencies, and the effect of this spread in frequencies is that the time average of E1 into E2, I have two waves, and the time average of the product of these, of the displacements or of the electric fields of these two waves is going to be less than this number as a consequence of the fact that we have a spread in frequencies. So, the spread in frequencies is going to cause this time average to be less than this value which is predicted when there was a single frequency only. So, we can incorporate this by rewriting this formula as follows: E1 t, E2 t, the time average of this is going to be 2 root 2 I1 I2, exactly the same as this when I have a single frequency, but we now introduce an extra term over here C12, and then we again write this over here cos phi 2 minus phi 1, where this term C12 the mod of this is less than or equal to 1, and it is going to be less than 1 when we incorporate the fact that there is a spread in frequencies in both E1 and E2. We have already seen that by definition C12 has a value 1 when E1 and E2 are monochromatic, that is, they have only a single frequency which is exactly the same for both of them. Okay. So, this number C12 we shall call the degree of coherence or the coefficient coherence coefficient of coherence. So, we shall refer to this as the coefficient of coherence or the degree of coherence or just the coherence. Okay. So, C12, the number which we have introduced over here, this quantifies the degree of coherence between the two waves E1 and E2. Okay. If these two waves have exactly the same frequency, the coherence C12 has a value 1. So, if if this has a value 1, the two waves are said to be exactly coherent, perfectly coherent. Now, I have already told you, and we are going to see an example shortly. If I incorporate the fact that there is a finite spread in frequencies for this and for this, then the value of C12, the modulus of C12 is going to be less than 1, and this refers to a situation which the two waves are said to be partially coherent and we could also have a situation where this coefficient is 0 and the two waves are then said to be incoherent. Let us now discuss examples of two waves which are coherent, perfectly coherent, incoherent and partially coherent. I will just give you simple examples to just show that this whole thing makes sense. The examples that we will consider are not realistic, just they have been constructed just to show you that this whole thing makes sense and give you an idea of how you can go about calculating it. Okay. So, perfectly coherent, we already know that if I had only a single frequency, if I have a wave with only a single frequency, so I have two waves E1, E2, both of which have only a single frequency omega, then the two waves are perfectly coherent. Now, absolutely incoherent, let me give you a situation where I have two waves which are absolutely incoherent. If this such a situation is very simple to construct. So, I will show you one situation. So, consider E1 So, we are considering a situation where I have two waves which have got two different angular frequencies omega 1 and omega 2. Right. So, we are considering two waves which have got two different angular frequencies, and the quantity which we would like to calculate now is the product of E1 t and E2 t. Now, we all know, we have discussed this, that if I take E1 and E2 to be sinusoidal waves of two different angular frequencies, this product is going to turn out to be 0. So, waves of two different angular frequencies are incoherent. So, we do not have interference in such a situation, because the term which is responsible for interference is exactly 0. The product of cos omega 1 t and cos omega 2 t, if I do a time average of this product, I get 0. So, we have seen one example, we have seen an example where we have perfect coherence, the two frequencies, the two waves are exactly monochromatic, only one frequency and the two frequencies are exactly same. Then we considered a situation which is incoherent. So, I have two waves of two different frequencies which are monochromatic and two different frequencies. So, when I multiply them and do a time average, I get 0. Now, let me give you a simple example, somewhat artificial example of two waves which are partially coherent. So, let us consider E1, the first wave. So, in complex notation, I will write the first wave E1 t as A1. So, I will write the first wave as A1. It is a superposition of two frequencies. So, A1 e to the power I omega t plus phi 1 plus e to the power I omega prime t plus phi 1. So, we have a wave E1 which is a which has got two frequency components. So, in the complex notation I have written E1 as A1 e to the power I omega 1 t plus a phase phi 1 plus e to the power I omega 2 t plus a phase phi 1, plus the same phase phi 1. Now, let me also write another wave E2 which is again a superposition of the same two different frequencies. But the phase could be different. So, we have two waves E1, E2. E1 has two frequency components omega and omega prime. E2 also has two frequency components omega and omega prime. And we would like to calculate the time average of E1 t into E2 t. Remember, the time average that we are interested in is the time average of the real wave E1 into the real wave E2. So, you could take the real part of this, real part of this and do the time average, or you could do the whole thing in complex notation. You have to be a little careful there. So, let me just straight away write down the result because we know all the required ingredients, but before going on, okay, let me write down the result first. So, the result here is as follows. When I multiply this with this, so when I multiply E1 with E2, the real part of E1 with E2, I will have one term which will come from the product of this with this, and these are oscillations of the same frequency, but with different phases, and the time average of the product of these two oscillations of the same frequency, but different phases we know is going to be A1, A2. The time average of oscillations of the same, this is going to give me a cosine term, this will also give me a cosine term. So, I will have a time average of cos square, and that is going to give me half into cos phi 2 minus phi 1, where phi 2 is the phase of this, phi 1 is the phase of this, and I will get a factor of half. Similarly, when I multiply this term with this term, you see I have to multiply this and this. So, I will have a term from here and here. This is going to give me exactly the same thing because this is A1 into an oscillation of frequency omega prime, this is A2 into an oscillation of frequency omega prime. So, same frequencies, when I multiply them and take the time average, I will get a cos square term which is going to give me half. So, half plus half, half from here is going to give me 1. So, this is what I get. Now, the cross term between this and this, it is a product of two different frequencies. When I take the time average, I get 0, this we have just seen. Similarly, when I multiply these two contributions, again I will get 0. So, the time average of the product of E1 into E2 is going to give me A1 into A2 into cos phi 2 minus phi 1. Now, we have to write this in terms of the intensity of this wave and the intensity of this wave. So, let us ask the question, what is the intensity of this wave? To find the intensity of this wave, I have to square this and take the time average. When I square this, I get A1 square. The time average of the square of this is half, time average of the square of this is also half. So, I get 1. The time average of the cross terms, these are two different frequencies. So, the time average of the cross terms are going to be 0. So, when I square this, and take the time average, I am going to get A1 square into half and another half here. So, this is going to be, so the intensity I1 is A1 square. Similarly, the intensity I2 is going to be A2 square. So, I can write, finally I can write the time average of E1 t into E2 t as the square root of I1 into I2, and I have this factor cos phi 2 minus phi 1. So, now let me go back to the definition. Let us ask the question, what is the coherence of this wave over here. So, to determine the coherence, we have to compare this with the definition. So, the definition of coherence is shown over here. Coherence, let me again remind you, coherence is defined as follows. If I have two waves E1 and E2, where E1 and E2 both have only a single frequency which is the same. So, if E1 and E2 are both pure sinusoidals of a single frequency, then the time average of E1 into E2 is 2 times the square root of I1 I2 cos phi 2 minus phi 1. So, it is the square root of the product of the individual intensities into cosine of the phase difference, and there is a factor of 2 over here. Now, if these are no longer monochromatic, if they are no longer pure sinusoidal waves, what I told you is that you have to modify this time average. So, this time average can now be written as C12 into whatever we had when there was only a single frequency in both E1 and E2, and C12 is what we use to quantify the degree of coherence, the coefficient which tells us how much coherence there is. So, we have to compare this expression with what we have just calculated in the situation where the wave is not monochromatic, but has two frequency components. And when the wave has two frequency components, when both E1 and E2 have two different frequency components, we found that the time average of the product of E1 and E2 is square root of I1 I2 cos phi 2 minus phi 1. So, comparing this with the definition of this coherence, the degree of coherence C12, we see that in this particular situation the degree of coherence C12 has a value half. So, what we see over here is that if I have a wave which is a superposition of two frequency components, the degree of coherence or the coherence coefficient falls from the value 1 which we have when the waves are monochromatic. When there is only a single frequency, it is perfectly coherent. Now, when I have two frequency components, the coherence falls to a value which is half. Okay. So, we have just considered an example where there are two frequency components. In reality, light or any other wave is going to have a spread in frequencies. So, in reality there is going to be an average value omega bar, and there will be a spread in frequencies around this value. And what I have tried to show you by doing this exercise is that in such a situation where there is a spread in frequencies, the coherence is going to fall. It is not going to be 1, it is going to be less than 1. The degree of coherence is going to be less than 1. So, that is the key point which I have been trying to convince you through these simple examples and simple and somewhat artificial possibly examples and then calculations. Okay. So, now let us ask the question, what is going to be the observable consequence of this, the fact that the coherence has fallen, what is going to be the observable consequence of this. So, let me now go back. Let me go back to the basic formula which we have for interference. So, let me now go back to the basic formula that we have for interference, and so the basic formula governing interference is again shown over here, and this formula now gets modified. So, when you are using partially coherent light, the intensity of the resultant of two waves is I1 plus I2 plus 2 root I1 I2, and now you have the degree of coherence cos C12 and cos of the phase difference phi 2 minus phi 1, right. Right. So, in this situation where we have perfectly coherent two perfectly coherent waves, C12 the coherence is 1 and the maximum intensity is what I have shown over here, and the minimum intensity and the maximum intensity, they are both shown over here, the maximum and the minimum. Now, the effect of this coherence of this partial coherence. So, if C12 the degree of coherence is less than 1, the main effect is it reduces the difference between the maximum and the minimum intensity, it reduces the contrast of the intensity pattern. So, there is the concept of something called the visibility, which is defined as follows. Let me introduce this new concept, new quantity called the visibility. The visibility is defined as follows: I max minus I min divided by I max plus I min. So, what does the visibility tell us? The visibility tells us how sharp, how much contrast do we not how sharp, how much contrast do we have in our fringes, how bright are the fringe is the fringe pattern. If the fringe pattern, if the whole field of view is more or less nearly uniformly distributed, the difference between the maximum and the minimum intensity is going to be very small. So, the visibility is going to be small, whereas if the fringe pattern is very bright, then the difference between the maximum intensity and the minimum intensity is going to be very large, and the visibility is going to be a large number. Visibility is a dimensionless number, remember, same as so is the coherence. The degree of coherence is also a dimensionless number. The visibility is a dimensionless number which can be directly measured from the intensity from the fringe pattern. You have to measure the intensity at the place where it is brightest in the fringe pattern, measure the intensity at the place where it is the darkest in the fringe pattern, and from there you can determine the visibility. So, for the situation where I have two waves of exactly the same intensity I1 and I2, which is the situation which we have been considering in both the Michelson and the Young's double slit experiment, we have been dealing with waves where the two we have been dealing with the situation where the two waves have nearly equal intensity. In such a situation, in the presence of this coherence, the degree of coherence factor which arises when we use partially coherent light, let us calculate the visibility. So, in such a situation, the maximum intensity that you have is 2 I1 plus 2 I1 into C12. So, I max, the maximum intensity, the minimum intensity is when the cosine term is minus 1. So, this will be 2 I 1 minus 2 I 1 C 1 2. We have assumed that I 1 and I 2 are same, and we have calculated the the maximum and the minimum intensity. Using this over here in the expression for the visibility, the visibility is equal to, so when I take the difference of these two, I will get 4 I 1 C 1 2. When I take the sum of these two, I will get 4 I 1, which is just the same as the degree of coherence or the coherence coefficient. Okay. So, the visibility is something that you can measure from the fringe pattern. Let us measure the degree of coherence. So, this tells us how, this gives us a method by which you can measure the interference. Interferometry gives us a method by which you can measure the degree of coherence of the light, of the wave that you are dealing with. And so, coherence has a very intimate link with the phenomena of interference. Now, let me go back. So, in the last few lectures we have been discussing a few cases of particular situations where we have interference. So, let me go back to these situations that we have been discussing. So, the first situation that we discussed was the Young's double slit experiment. In the Young's double slit experiment, let me just in the Young's double slit experiment, if you remember, we had a source which emitted a wave. So, this was the source which emitted a wave, and then the wave front was incident on two slits. So, the wave fronts that come out from here are incident on two slits. The role of the two slits is that it divides the two wave fronts, it divides a single wave front. So, it takes the wave from two different parts of the wave front, and these interfere, these are superposed, these arrive at the screen by through separate paths, and on the screen you measure, you have the superposition of two different parts of the wave front through two different slits. So, you have produced two waves on the screen over here through the division of wave front. So, in the Young's double slit experiment, what you have done is you have this is, let us say this is a, these are two different, this is a wave front, you have taken two different points over here, and on the screen over here what you do is you superpose the electric field or the wave at these 2 points. So, these are the slits, and over here on the screen you superpose the electric field. So, we can call this is slit 1, this is slit 2. What you have over here is E1 into E2, and you take the time average of E1 into E2. Now, there is another point which comes in over here. Different points on the screen receive these two waves with different time delays. So, what you do over, what you achieve in the Young's double slit experiment is that you are able to determine the coherence between the wave at two different points, the two different points being the two different slits, right. So, you are able to determine the coherence between the waves at two different points, at which are the two different positions, which are the two slits. So, on the screen over here you essentially measure the coherence of the wave at these two different points. So, at the central position you measure E1 and E2 at the same instant of time, the time average of this. This is only at the center. If I move to a different point on the screen, if I move to this point on the screen, I will be measuring E1 and E2 with different time delays, because the paths which they have to propagate are different. So, over here I would be measuring E1 and E2 with different time delays. Let us focus on the interference that we get on the intensity at the screen over here. So, at the center of the screen, we are measuring E1, the electric field here, the wave at this point, E2, the wave over here, the product of this, and the time average is what is measured over here. So, what we are doing is we are measuring the coherence between the wave at two different positions at the same time. We can refer to this as spatial coherence. So, we have put a displacement in the position and we are measuring the coherence between the wave at two different points at that particular displacement. So, the point at the center of the screen over here is measuring the spatial coherence of this wave, the wave that is produced by this source, from this source over here. So, at the center of the screen you essentially measure the spatial coherence of the wave at between these 2 points, between these 2 slits. And we have already calculated this. So, we have calculated this quantity at the center of the screen. We shall take up this the interpretation of that in terms of coherence in the next lecture.